Hello everyone, this is our lecture on chemical formulas. And we're going to learn about two kinds of chemical formulas called empirical and molecular formulas. Alright, so let's start with the empirical formula. Um, these are both empirical and molecular formulas are ways of describing the elements that make up a compound. The empirical formula is not the one that we've been using up until now, so it might look a little unfamiliar. It's the lowest whole number ratio of the elements that appear in the compound. The lowest whole number ratio, all right? And so it will, like any formula, it shows the kinds of atoms that are in a formula, but in this case, it gives you a relative number of atoms of each type that make up the molecule or the formula unit, and not the actual number. So, in a molecular formula, an empirical formula will be reduced to its lowest whole number ratio, even if you're dealing with the polyatomic. So let's look at an example, and I think we'll make this a little more clear. Here is the formula for hydrogen peroxide, H2O2. The empirical formula for this compound is HO, because this is the lowest whole number ratio for the elements that appear in this compound. There are two hydrogens and two oxygens, but so in the compound itself. And if you want to write this as the lowest whole number ratio, you would just write HO or H1O1. Now I don't have it in the slide, but compare that to the formula for water, H2O. You can see that, well, you can't see it because it's not on the slide, but H2O is the empirical formula for water because it is the lowest whole number ratio, H2O. You can't simplify that like you were able to simplify this one, H2O2, into this more simple version. So the empirical formula is lowest whole number ratio of elements that appear in that compound, um, and it does not necessarily represent the actual numbers of elements that you would find. All right. So let's see an example. Um, the empirical formula would probably come up, if you will, in analytical chemistry when you have an unknown compound and you can do some kinds of experiments to determine what the elements are in the compound, but you don't yet know exactly what it is. And so that this sample question sort of comes from that. You have some unknown compound and you've done some experiments to determine that it's 30.4% nitrogen and 69.6% oxygen, but you don't really know what the makeup of the compound is yet. You just know that it's mostly oxygen and then some nitrogen. We want to find its empirical formula. The first step is to assume 100 grams, and we do that just to make the calculations easier. So I recommend that you do this too. You don't have to, but it makes your life easier if you assume that you have a 100-gram sample of this unknown compound. We are then going to convert that grams into a number of moles for each element. So if we had 100 grams of this compound and we know that it is 30.4% nitrogen, then we can take 100 grams times 0.34 to give us 30.4 grams of nitrogen in our hypothetical 100 gram sample. All right, and then we take the molar mass for nitrogen to convert that, which is 1 mole is 14 grams, and we convert this number of grams into a number of moles. So in our hypothetical 100 gram sample, we would have 2.17 moles of nitrogen. All right. Then we do the same kind of calculation for oxygen. Our hypothetical 100 gram sample times the percentage of oxygen expressed as a decimal, 0.696 from right here. That equals 69.6 grams of oxygen. We want to convert grams into moles, so we multiply by 1 mole of oxygen is 16 grams, and you get 4.35 moles of oxygen. So this would be the molar makeup, if you will, of our 100-gram hypothetical sample of this compound. 2.17 moles of nitrogen, 4.35 moles of oxygen. Okay? Now the next step is to look at those numbers that we saw right here, 2.17 and 4.35. If those moles are whole numbers, then those become the subscripts in for the elements to which it refers. That's not the case here. 2.17 is not a whole number, and 4.35 is not a whole number. So if the moles have decimals, then we divide that number of moles by the smaller of the two numbers calculated in step 1. So in other words, you divide each of them by the smallest of them. And then when you have, that's a sort of a math trick for converting things into whole numbers. Then we can use those as subscripts. So let's see how that plays out. We had our, remember there was 4.35 moles of oxygen and 2.17 moles of nitrogen. 2.17 is smaller than 4.35, so as I said, we're going to divide each of them by the smallest of them, which means we put 4.35 moles of oxygen over 2.17, and if you do that division, you get 2, which is a whole number. All right, so, and of course, if we put 2.17 over 2.17, remember I said to divide each of them by the smallest of them, we would get 1. All right, so that means there are 2 moles of oxygen and 1 mole of nitrogen, which means your formula is NO2. This is your empirical formula for this compound that we started this sample problem with. All right. Now we'll have some more opportunities to practice problems like this, so fear not if that still is a little bit confusing. We'll be practicing it in class Friday and probably on Monday and Tuesday as well. All right, let's touch quickly on the molecular formula. This is the one that you are more familiar with. The molecular formula is the one that we use kind of every day. It's the chemical formula we've been using up until now, and it basically gives you an actual count of the molecules that make up a compound. So if I look back at that hydrogen peroxide example from earlier on, the empirical formula, remember, for H2O2 was simply HO. The molecular formula, the actual formula, was H2O2. All right, so you see the difference? All right, now what we want to be able to do is find the molecular formula because, again, thinking back to that hypothetical example where you had an unknown compound and you did some experiments to determine what it was made up of, you were able to find an empirical formula. Now you want to use that empirical formula to find the actual molecular formula. So here's an example that we can work through in this regard. Let's say we have a compound. We know we've done the work to determine its empirical formula to be CH3O. And then there's another kind of analysis that we did to determine the molar mass of the actual compound to be 62 grams per mole. All right? So we have 2 pieces of information given to us. We need 2 pieces of information in order to determine the molecular formula. We need an empirical formula, which is given to us here, and we need the molar mass of the compound, which is given to us here. All right, so, and I just reprinted that information up here so that we can keep it in our minds. This is what's given to us up here. Step 1 is to calculate the mass for the empirical formula. We want to find basically the molar mass for this empirical formula. It's got 1 carbon and 3 hydrogens and 1 oxygen. So if we calculate, we do our standard basic molar mass calculation for 1 carbon, 3 hydrogens, and 1 oxygen, you get 31 grams per mole. Okay, we've done this many times, so it should be comfortable. Only this time, you're calculating this for this empirical formula that was given to us in the problem. The next step is to compare the given molar mass to the thing that you just calculated, and that will give us a ratio. So we just calculated on the previous slide, we found that the mass for this empirical formula was 31 grams per mole. And the given molar mass for the compound is 62 grams per mole. We're going to compare these two to get a ratio. So we put 62 over 31. You put the molar mass of the actual compound over the calculated mass that you just came up with. 62 over 31. So 62 divided by 31 is 2. So this ratio is 2. All right, so then we're going to multiply the empirical formula right here by our ratio, 2, to get the molecular formula. So we take our CH3O, that's our empirical formula, and we're going to multiply, basically, effectively multiply it by 2. So we distribute this 2 across. We have C2H6O2. This is the molecular formula for the compound. And this also gives us a nice demonstration of the comparison or the difference between a molecular formula and an empirical formula. Do you see how they're related? This empirical formula is a simpler version, if you will. It's the lowest whole number ratio of this molecular formula. All right? So this is your molecular formula, here is your empirical formula, and those were the steps that we followed to get there. Now we'll be practicing these over the next couple days, so take notes on this, write it down, bring your questions to class tomorrow, and we will proceed from there. That's it. Thank you.